Lab 4. An oscillating mass attached to a spring. In this lab, I observed the motion of an oscillating mass attached to the bottom of a spring. The mass is released from a point above its fully stretched length and to the left of the y-axis of the origin. This makes the mass move in an elliptical motion in that it is swinging like a pendulum in the x direction and bouncing up and down in the y direction due to the spring stiffness. The objective of this lab was to analyze the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The results of this lab are that the predicted motion of the mass followed the same pattern as the data received from Tracker. Therefore, the spring mass system satisfies the energy principle. The video that we analyzed in Tracker, which we can see here, begins with a point of release that is 7. So the point of release is above the fully stretched length of the spring, which is 7 meters, or sorry, 0.7 meters. And if we play the video, so this is slide 5, and we are setting that as our t equals 0. So we can watch this video. To the right, we can see the plotted x coordinates over time as well as the y coordinates over time, and here below are both x and y coordinates with respect to t. From these graphs we can deduce a few things, but most importantly we're going to be using them to find the average period of oscillation. But before we get to that, let's go over the fundamental principles we will use in order to analyze the motion of the mass, starting with the momentum principle, which predicts a new velocity and position of spring mass. So we're going to use that to find all the velocity values as well as the new, predicting the new positions of the mass. So that is, the final velocity is equal to the initial velocity plus the quotient of the net force over mass, all times the change in time, delta t. The energy principle states that the change in energy of a system is equal to the work done by the surroundings on the system. So the change in energy is equal to the change in kinetic energy plus the change in potential energy. In this case, the potential energy that we're going to be referring to is the gravitational potential energy, and these should sum to 0, meaning that energy has not left the system. So, calculating the spring force. Oops, sorry. So, sorry, the initial conditions we need to put into Python include the mass of the ball, which is 0.402 kilograms, the initial position of the mass, which you can just see are these first two x and y coordinates found in Tracker. So you can see the ball's initial velocity is 0, and we're starting from t equals 0. So to find the spring stiffness using the period of oscillation, which is taken from the average of the first 3 wavelengths of the position versus time graph in Tracker. So that value over 3 would give you a rough estimate of the average period of oscillation. So we can see that t is equal to 2 pi over omega, and omega is equal to the spring stiffness over the mass. So we know that the average period time is 1.614 seconds, which is equal to 2 pi times the square root of the mass, which we know is 0.402 kilograms over the spring stiffness. Solving for spring stiffness, we find that it is equal to 6.06 kilograms per meters per second squared, or kilogram meters per second squared. Sorry. The way we calculate the compression or stretch of the spring, and L naught, the relaxed length of the spring, is by setting we know that the weight force is going to be equal to the spring force, and the spring force is equal to the spring stiffness times the compression of the spring S. So solving for S, we find that it is 0.64 meters, and from that we can find the relaxed length of the spring, which is 0.13 meters. Plugging all of this into our Python code, we move on to the kinetic, or the energy principle parts of the code. So the kinetic energy is equal to 1/2 the product of the mass and the velocity squared. The gravitational potential energy is equal to the product of the mass, the gravitational constant, and the height above the surface of the Earth, but we're so close to the surface of the Earth we can ignore h for now. Gravitational potential energy is equal to 1/2 the product of the spring. Sorry, I meant spring potential energy is equal to 1/2 the product of the spring stiffness and the spring compression squared. Okay, so taking this Python code and we will run the module. I will show you this graph momentarily, but for now we can see the blue ball, which represents the mass, is moving in an elliptical orbit, oscillating. So the blue arrow represents the spring force, the black arrow represents the weight force due to gravity, which is F equals mg, also known as the gravitational force. The ball, as I said, represents the mass. If we go to this graph, we can see the blue line closer to the yellow one represents the changes in kinetic energy. The red line represents the changes in the spring's potential energy, and the green line is the gravitational potential energy. The yellow line is the total energy of the system, and in accordance with the energy principle, it is summing to 0. So what does this mean? Because every agent is included in the system, there are no outside agents doing work on in the surroundings working on the system. Therefore, energy is conserved and the energy principle is satisfied. For the what-if analysis, I plotted these graphs from Tracker in Excel separately in order to analyze the differences in period duration between the period of oscillation of X position versus Y position. I found that the period of the X position was equal to 1.52 seconds, while the period of Y position is 1.614 seconds. This means that the oscillation in the Y direction lasts for 0.094 seconds longer than an oscillation in the X direction, And this difference in period length is due to the fact that the equation for the period in the y direction includes the mass attached to the spring as well as the spring stiffness, while the equation for the period in the x direction includes the length of the spring and gravity. Thank you for your time. This has been Lab 4.